Good afternoon, and thank you for coming. I'm sorry, like the previous speaker, I've changed the talk, but I think I made it more interesting for you to judge. So I'm not going to talk about how you use formal verification to secure AI. I'm going to talk about the opposite. I'm going to talk about how to use AI to make formal verification easier. And actually, this talk applies not just for formal verification, it applies for fuzzing and others. So please listen. I'll save some time for questions. So about me, I'm a co-founder of Certora. Feel free to ping me. This talk is actually not done by me. It's done by three amazing people on our team, Naftali, Yaroslav, and Johannes. And they're not here, but are available to answer questions. It's a small project that we have done. We are incorporating into our open source tool. We can give you the source already, or if you want, you get it as part of the open source repository of the Certora prover. So there are many, many tools in this space, and we think that this work applies to many of them. Here, we listed some of them. So Slither is the sort of a very mature static analysis tool, fairly easy to use. The problem is it doesn't provide a lot of security. It's very, very general. Also, it's hard to use it for bugs, and you can integrate into CI. Foundry is a fuzzing tool. There's also Echidna. These are good tools. They give more coverage than static analysis, but a bit harder to use. Then there's K-Lean interactive term provers. There's also Audit Agent, which is a recent, and many others. I'm sorry I didn't have to list them all. But these are tools based on AI to find bugs. And I listed the one by Nethermind, but there are others. I apologize. And our own tool, Prover, Certora Prover, which is open source. This is actually a tool that we think it's very, very usable for developers. It checks the code. At the moment, we made it available for EVM, SVM, and WebAssembly. And it's basically giving you high security, and it's still easier to use. But the purpose of this talk, it makes it even more easier. So maybe just sort of talk about what are the things that people are used for security. So obviously, people are using manual auditing. This is the standard. And we know that auditors can find a lot of issues. But the problem is auditing, it's a human process, so it's error-prone, and it could be expensive and time-consuming. Testing, fuzzing, it's great. You can automate it, but you miss some of the bugs, and it's very hard. It also can be expensive. Formal verification has been used in other industries, for example, safety-critical system. It's provide a guarantee, but it's really, really expensive in terms of human effort and computational effort. And AI checks, it's something which, of course, exists before, but now with the AI, it's getting more and more popular. So what we want to do, we want to integrate it into formal verification. This is the definition of formal verification come from Wikipedia. It's this method to give you a guarantee about your code. But we take from this the actual definition that was given to us by Ernesto from BGD. It's a mechanism that actually increases your security or your confidence in your code. So somehow it's something that allows you to go to the unknown part of your code. It gives you more security of your code. So it increases your trust. And this is, of course, a nice quote by Vitalik. This game sort of showed that if you use formal verification, open source, you increase the trust in the software. And also Tolly, looking actually after using our prover, essentially saying that this can be also useful for the Solana. Okay, so for the purpose of this talk, I'm going to do something which basically I'm saying formal verification is good for proofs, but it's also good for bug finding. And I'm going to show you that actually formal verification, in addition to the fact that it's used for proof, it's actually useful for bug finding. Okay, so why actually do we want to use AI for formal verification? And why is formal verification not heavily used if it's so useful? So there are many answers, but I think one particular answer that formal verification is considered hard. And a lot of people, I've studied computer formal verification for a long time, they say this is sort of the hardest problem in computer science. And it's hard from a computational perspective, but it's also hard in terms of learning curve. Okay, so these are many things that sort of go to you that you are starting formal verification. Probably the most difficult part is the mindset. You have to change your mindset. When you are a hacker or when you are a programmer, you have some kind of adversarial thinking, which is very, very useful. You think, how do I break it? When you're doing formal verification, you need this adversarial thinking, but you also need to think about what properties it is. And actually, some people say that the best hackers are the ones which think about both. But it's sometimes hard to find. So you need to think in terms of what is the code is expected to do. And then you can use it with tools or with humans to break this thing. So you need to think, and another thing that you need to do, you need to think declaratively. You need to think of what is this code as opposed to imperatively. And we know it's incomparable. You know, we think imperatively, I go someplace, I need to do something. It's sometimes more natural. But somehow, and for example, when we work with clients, sometimes we come with a property, we say, we wish we knew it before we wrote the code. Because you have to come with these kind of properties, and it's hard for people to do that. As a result, sometimes people abuse formal verification. Our tools are that. And there are many ways you can abuse formal verification. For example, you can prove things which is tautology. You prove that 7 is greater than 5. That's great, but it's not saying anything about your code. And also, diagnosing formal verification is hard, because basically formal verification can do something very, very useful to you, but then it gives you an example, and it's hard for you to understand what it means. So that's why formal verification, and we see some kind of a learning curve. Somebody learns formal verification, and it takes him or her some time. So what do we want to do? In the purpose of this talk, and we have only done baby step, we have actually added this AI-based formal verification. The idea is a formal verification, but not the human is writing the properties, the system is writing the properties. So the system is trying to infer the properties that a smart human is writing. Okay, so how does it work? So we start with the general DeFi knowledge. We basically have a database of information. We take the design of the code. We take the code itself. And we also take any documentation that you have in mind. And this is actually where the smart part starts. You infer a property. We have a very simple language that we build, which is, you can think of something like Swivel or something like this. It's a language that allows you to write things that you cannot exactly code, but it's similar to code. It describes the requirement on your code. I'll give you an example soon. Then we use a normal compiler. We essentially, this is not very smart, but still you have to do it. You have to compile into the CVL, into our own domain-specific language for writing the properties. And then we run the Certora prover. This is an automatic tool. You can run it on the cloud. And if it verifies the property, you know it verifies. If you trust it, you increase your confidence in the code. The interesting thing, what happened when it's violated? There, we use the AI again. Why do you use the AI again? Because we want the AI to help us diagnose what is the problem. Because we want the AI to explain, actually, and AI are very good, but they are very local. And they can make terrible mistakes. But it's not so bad. We run it, and we will check it, okay? So basically, this gives you this potential exploit scenario that a human needs to check. And then, if this error is real, then you, have, in fact, apply the manual fix, and then you run the Certora prover. So I give you a few examples. As I said, we are doing a really, really baby step at this point. So please bear in mind that we need to run it on way more examples. But we have been running it on few examples based on things for the public domain and based on manual audits and formal verification projects that we have done. So this is, of course, example everybody knows. It's the Open Zeppelin transfer. It's a baby example, but it's good to show you what we do. So we take the code, we take the transfer function, we basically, okay. We take the code, we take the transfer function, and what we do, we take the code itself and we hide it. We don't show the AI the implementation itself because we want it actually to find something which is the intended behavior, not the executed behavior. But we show it all the other part of the code, and then we also show, of course, the documentation. And we ask the AI to infer what is the intended behavior of this code. So this is what we do. You see this thing? Okay, and let's see what it's inferred. Oops. For some reason it doesn't move. Don't know. Okay, so it infers very simple property. It infers that the total supply is unchanged. It's still a simple property. You see that, and it also infers potential exploit scenario. Okay, it infers that a buggy transfer might increase the total supply, allowing it take. So it infers both of these. It infers the spec, and you see this spec is not actually written exactly in Solidity. Bear in mind, we have actually some extension of Solidity to express some things that to allow you to write the properties. But it's not the full power of CVL. It's something much weaker. And you see, this is what it infers. It's a very interesting case, but it's very, very simple. We also apply to something a bit more real. Okay. Oh, sorry. This is the code which is generated by our compiler. You see, this is Certora verification language. If you don't know Certora verification language, ignore it. There's some boilerplate code. It's essentially writing on a bytecode. It is details. It's details. Think about it. It's some details. But the nice thing about it, you don't need to know that. It's automatically generated from the high-level spec. And I imagine you can do it for fuzzer like Foundry and Kidna. We have not done it. But I'm sure you can do something similar. OK, so let's look into more interesting example. We work with clients before they deploy the code. This is a beautiful client we have been working, I think, for 4 years, Balancer. I'm sure everybody knows them. And we work with them together with other auditors. And we are proud of finding the most interesting bugs, preventing the most interesting bugs. And here is a very interesting bug which we prevented at this point without AI, with our humans, of course. And it's a critical bug. I won't be able to explain, but the idea, it's written in our blog and actually acknowledged by the Balancer team. It's essentially allow you to use the token in a way that you actually steal all the money. It's a very, very tricky situation. I wouldn't be able to find such a bug. Okay? How did we find it? So we ended up writing a property. You see, we wrote a property. It says this is the property, and essentially the property says that if you have shares, you have asset to cover for the shares. So it's a very natural property. And then you see we write it in our CVL. It's an invariant. It's an invariant. You can write it. So it's basically, you see, in CVL, you write invariant, which are independent of the function. So you see that here, we say that if you have total shares, then you have assets. It's a very, very sort of natural property. And this natural property is violated in a very rare situation. And the prover automatically finds this violation. But the human had to write this property. Okay, so somebody in our team has to write this property. Okay, so let's see what the AI inferred. So the AI inferred something actually simpler. The AI inferred that basically the amount of asset doesn't change. It's infer a simpler property. And let's wait a second. And it's also infer exploit. It's interesting. It also infers an exploit. You see, if the buffer asset could be changed, in fact, it's interesting. It infers, and it infers it, of course, based on history of bugs that happen. So basically, this thing knows about many, many bugs that happen. So the AI inferred the property, and infer also the exploit. And you see, this is the generated CVL code. It's technical. It doesn't matter. It's basically generated automatically by the compiler. So it's interesting. This is a case that a bug that somebody could have found without using us at all. Okay? I can tell you, you could save money. Okay, so that's the idea. I want to give some time for question. So further work, we want to use it internally. We are doing good job, but I can tell you our audit takes us a long time. I know, thanks. Our audit takes us a long time. So we want to shorten our audit. And the idea is we're going to use this tool initially, and after that, add things by human. And hopefully it will speed our internal work. We also want to open source it. We only use Anthropic. There are many other LLM. We want to support Foundry and Echidna. And there are some things that you cannot write in this language, for example, and this, for example, properties of internal functions and things like that. So I'm almost done. I just want to, before I go to the question, I want to, don't get this talk wrong. So this talk doesn't prevent, we still need auditing, we still need fuzzing, we need everything. Okay, I don't want to confuse you. This talk is actually giving you an extra security layer. You can use our tool to use this AI-based together with our tool or fuzzing and others. It just gets another layer. I'm not proposing it instead of everything you have. And finally, I think it's interesting that basically AI allows us to do more automation of security. So I'm ready to take questions. Please ask me some questions. Yes?
Yes, hello. Thank you, Professor, for this interesting talk. I just wanted to ask about the false positives. So how often does it say that there's an exploit when there actually, when a human studies it, there's no exploit?
So notice that in this case, and that's now something interesting, somebody could think of formal verification and AI as complementary. AI is very, very local, but it makes mistake. Formal verification doesn't make mistake, okay? When we prove the property up to a bug in our tool, it is proved, okay? And when we have a violation of it, up to a bug in the rule, it is a violation. Otherwise, you will complain a bug in our tool. So the formal verification has a scaling issue, but the formal verification always gives you the exact answer. LLM give you a lot of noise. But this noise you can check. Of course, it could be confusing if it gives you a bug which is not understandable. But the false positives are being sort of handled by the formal verification tool.
Very interesting talk. Thank you. One of the slides said your AI model already had knowledge of DeFi. Can you talk a little bit about whether you found an existing model that had DeFi knowledge, or did you train one yourself? And if you did train it, what is the data set you used to train? Thank you.
Yes, that's an excellent question. So the question is, how do we get AI models? So it's very clear that in many domains, including us, there's very small data. Companies like OpenAI, they do a magic job by basically putting a lot of smart engineers to collect this data. We are, at the moment, using very, very simple data. It's based on all open source, and it's based on the repository that we have. And of course, we have a little bias to use our thing because we understand it more. But of course, we want to use more. And we want to leverage community. And at some point, if we have enough budget, we'll probably put engineers to collect data and to gather data ourselves.
Thank you. It was a very nice talk. I'm just wondering, I think it's a bit related to the exploit question, but separately, how many of the specifications that were generated by AI were actually correct? Did they actually capture what you were intending from whichever function you were analyzing at time? So does it generate a lot of completely garbage, even things that might not be syntactically correct even?
So for us, the one thing that we did, for good and for bad, we picked a very, very simple language for writing the property. So if you generate CVL, you're definitely right. CVL is very expressive. It's allowed to write. We decided to go about the long-hanging fruit. So by definition, the properties that we infer are small. But I want to be fair with you. We have not done enough experiment to say, I imagine you're probably right at some point. It depends also which audit we go and depends on which thing we go. I'm sure there will be some noise. I totally agree, and we have to see.
Okay, thank you.
Thanks, everybody. Thank you for the talk. We will have this work very soon available. Thank you very much.